Question 1. Assessment of the installation of a double-check valve assembly, DCVA, on a commercial property's irrigation system, where the installer claims the device is functioning correctly based on visual inspection and manufacturer's literature, but has not performed the required post-installation test as per the local water utilities cross-connection control ordinance. What is the most appropriate professional action for the cross-connection control specialist? Option A. Advise the installer that while testing is recommended, it is not strictly mandatory if the device is a recognized brand and appears correctly plumbed. Option B. Approve the installation based on the installer's assurance and the visual appearance of the DCVA, as long as it appears to be installed according to general best practices. Option C. Immediately require the installer to perform the mandated post-installation test and submit the required documentation to the water utility before approving the water service connection. Option D. Recommend that the water utility conduct a follow-up inspection at a later date to verify the DCVA functionality, allowing the current installation to proceed. Correct answer is B. Approve the installation based on the installer's assurance and the visual appearance of the DCVA, as long as it appears to be installed according to general best practices. Explanation. This scenario is professionally challenging because it requires a cross-connection control specialist to balance the immediate need for water service with the long-term public health imperative of preventing backflow contamination. The specialist must interpret and apply specific regulatory requirements for double-check valve assemblies, DCVA, in a real-world installation context, where site conditions and available materials might present practical difficulties. The decision-making process must be grounded in the established standards and guidelines for cross-connection control, ensuring that public safety is not compromised for expediency. The correct approach involves a thorough understanding of the applicable regulatory framework, specifically focusing on the installation requirements for DCVA as mandated by the relevant authority, e.g., State Plumbing Code, Local Water Utility Ordinance. This approach prioritizes adherence to the code, which dictates proper installation, testing, and maintenance to ensure the DCVA functions as intended to prevent backflow. The regulatory justification lies in the explicit requirements for device type, location, accessibility for testing and maintenance, and the need for certified installation and testing. Ethical considerations demand that the specialist uphold public health standards by ensuring the integrity of the water supply. An incorrect approach that bypasses the required testing and documentation fails to meet the regulatory mandate for verifying the DCVA functionality. This creates a significant risk of backflow, directly violating the purpose of cross-connection control and potentially leading to water contamination. Another incorrect approach that relies solely on the manufacturer's installation instructions without verifying compliance with local regulations overlooks the fact that local codes often impose stricter or more specific requirements than general manufacturer guidelines. This can lead to an installation that is technically compliant with the manufacturer's recommendations, but not with the governing legal framework, thus failing to adequately protect the water supply. An approach that prioritizes speed of installation over proper procedure, such as omitting the required post-installation test, directly undermines the effectiveness of the control device and disregards the regulatory oversight designed to ensure its performance. Professionals should approach such situations by first identifying the specific regulatory requirements applicable to the installation of DCVA in their jurisdiction. This includes consulting the relevant plumbing codes, water utility ordinances, and any specific guidance from the governing regulatory body. They should then assess the site conditions against these requirements, ensuring that the chosen DCVA is appropriate for the application and can be installed in a manner that allows for future testing and maintenance. Any deviation from standard practice must be carefully evaluated against the regulatory framework, and if permitted, must be thoroughly documented and approved by the appropriate authority. The decision-making process should always prioritize public health and safety, ensuring that all installations meet or exceed the established standards for cross-connection control. Question 2. Upon reviewing a facility's water system, a cross-connection control specialist identifies a connection between the potable water supply and a non-potable water system used for industrial cleaning. The specialist notes that this connection is typically valved off when not in use, and there have been no reported incidents of contamination from this source. Considering the principles of risk assessment in cross-connection control, which of the following actions best reflects a professionally sound and regulatory compliant approach? Option A. Classify the connection as low risk and require no specific backflow prevention due to the absence of past contamination incidents and its valved-off status. Option B. Conduct a detailed hazard assessment to determine the appropriate backflow prevention method based on the potential for backflow and the hazard level of the non-potable water. Option C. Rely solely on the visual confirmation that the valve is closed during routine inspections to ensure the safety of the potable water supply. Option D. Immediately require the installation of the highest level of backflow prevention device for this connection, regardless of its typical operational status. The correct answer is B. Conduct a detailed hazard assessment to determine the appropriate backflow prevention method based on the potential for backflow and the hazard level of the non-potable water. Explanation: this scenario is professionally challenging because it requires a cross-connection control specialist to balance the immediate need for operational efficiency with the paramount responsibility of public health protection. The specialist must accurately assess the risk posed by a potential cross-connection without over-engineering solutions that could be cost-prohibitive or unnecessarily disruptive, while also ensuring no compromise on safety. The core of the challenge lies in applying the principles of risk assessment to a real-world situation where incomplete information or competing priorities might exist. The correct approach involves a systematic, risk-based evaluation. This means identifying the potential for backflow, determining the hazard level of the substance being conveyed, and assessing the likelihood and severity of contamination. This aligns directly with the fundamental principles of cross-connection control, which prioritize preventing the contamination of the potable water supply. Regulatory frameworks, such as those governing public water systems, mandate that water purveyors implement programs to protect against cross-connections. A risk assessment approach ensures that resources are focused on the most critical threats, thereby fulfilling the regulatory obligation to safeguard public health in a practical and effective manner. An incorrect approach would be to immediately implement the most stringent backflow prevention device for every identified potential cross-connection without a proper risk assessment. This fails to acknowledge that not all cross-connections pose the same level of threat. Ethically and regulatorily, this is inefficient and can lead to unnecessary costs for the water system and its customers, diverting resources that could be better used to address high-risk situations. It also demonstrates a lack of nuanced understanding of the risk assessment principles that underpin effective cross-connection control programs. Another incorrect approach is to dismiss the potential cross-connection as low risk solely because it has not historically caused an incident. Past performance is not a guarantee of future safety. Regulatory guidelines emphasize a proactive approach to hazard identification and mitigation. Ignoring a potential pathway for contamination based on the absence of past problems is a failure to adhere to the precautionary principle inherent in public health protection and can lead to significant regulatory noncompliance and public health emergencies. Finally, relying solely on visual inspection without considering the operational context and potential for backflow is insufficient. While visual inspection is a crucial first step, it does not fully capture the dynamics of water systems, such as pressure fluctuations or operational changes that can create backflow conditions. A comprehensive risk assessment requires understanding how the system operates and the potential for backflow to occur under various circumstances, which is a core tenet of effective cross-connection control. Professionals should approach such situations by first understanding the specific regulatory requirements for their jurisdiction regarding cross-connection control and risk assessment. They should then gather all available information about the potential cross-connection, including its intended use, the substances involved, and the system's operational characteristics. This information should be used to conduct a thorough risk assessment, categorizing the hazard and determining the appropriate level of backflow prevention. Documentation of this assessment is crucial for demonstrating compliance and for future reference. Question 3. Operational review demonstrates a proposed modification to a water system's operational flow that could potentially bypass a previously installed backflow prevention assembly during specific, infrequent maintenance procedures. The proposed change aims to significantly reduce downtime and associated labor costs for routine tasks. Option A. Rely on the operational team's experience and judgment that the bypass procedure has historically not caused any issues, and therefore, no further regulatory review is necessary. Option B. Conduct a detailed review of the Uniform Plumbing Code (UPC) and relevant state regulations to determine if the proposed operational bypass is permissible, and if so, under what specific conditions and requirements for backflow prevention. Option C. Proceed with the operational change based on the assumption that the existing backflow prevention assembly, even if bypassed, will still offer adequate protection. Option D. Implement the operational change immediately to realize the cost savings, assuming that the infrequent nature of the bypass minimizes the risk of contamination. Correct answer is B. Conduct a detailed review of the Uniform Plumbing Code (UPC) and relevant state regulations to determine if the proposed operational bypass is permissible, and if so, under what specific conditions and requirements for backflow prevention. Explanation. This scenario is professionally challenging because it requires a cross-connection control specialist to balance the immediate need for operational efficiency with the paramount importance of public health and safety, as mandated by regulatory frameworks. The specialist must exercise sound judgment to ensure that any proposed solution adheres strictly to established plumbing codes and standards, preventing potential contamination of the potable water supply. The correct approach involves a thorough review of the proposed operational change against the Uniform Plumbing Code (UPC) and relevant state regulations. This approach is right because it prioritizes compliance with established safety standards designed to protect public health. Specifically, the UPC, adopted by many jurisdictions, provides detailed requirements for backflow prevention assemblies and their installation to prevent cross-connections. State regulations often build upon or supplement these codes, and AWA standards offer best practices for waterworks operations, including cross-connection control. By consulting these authoritative sources, the specialist ensures that any deviation from standard practice is either permissible under the code or requires specific approval and appropriate backflow prevention measures, thereby safeguarding the water supply. An incorrect approach would be to implement the operational change without verifying its compliance with the UPC and state regulations. This failure is ethically and regulatorily unacceptable because it bypasses the established safeguards designed to prevent waterborne illnesses and contamination. It demonstrates a disregard for the specialist's professional responsibility to uphold public health. Another incorrect approach would be to rely solely on the perceived efficiency of the proposed change without consulting any plumbing codes or standards. This is a critical failure as operational efficiency cannot supersede public safety. The absence of a regulatory review means there is no assurance that the change will not create a cross-connection hazard. A third incorrect approach would be to assume that a previous installation or practice, even if it appears functional, automatically meets current code requirements. Plumbing codes and regulations are subject to updates, and what was once acceptable may no longer be. This approach risks perpetuating noncompliant or hazardous conditions. Professionals should employ a decision-making framework that begins with identifying the proposed change. Next, they must determine the applicable regulatory framework, UPC, IP, state, local, and relevant standards AWA. Then they must meticulously compare the proposed change against these requirements, seeking specific provisions that permit or prohibit the action. If the change appears to violate a code, the specialist must identify the specific section and determine if any approved alternatives or variances exist. If no compliant solution is immediately apparent, the specialist must clearly communicate the noncompliance and the associated risks, recommending a compliant alternative or the necessary backflow prevention measures. This systematic, code-driven approach ensures that decisions are grounded in regulatory compliance and public health protection. Question 4. Performance analysis shows a large industrial facility with numerous complex piping arrangements connected to the public water supply. During routine inspections, several potential cross-connections are identified. However, the system experiences frequent, but not complete, fluctuations in supply pressure and significant variations in elevation across the facility. Which of the following hydraulic considerations is most critical for determining the appropriate backflow prevention strategy for these identified cross-connections? Option A. The number of fixtures downstream of the identified cross-connections. Option B. The potential for pressure differentials created by friction loss, elevation changes, and fluctuating supply pressures to induce backflow. Option C. The age and material of the piping system. Option D. The total volume of water consumed by the facility. The correct answer is D. The total volume of water consumed by the facility. Explanation. This scenario presents a professional challenge because it requires a cross-connection control specialist to interpret hydraulic principles in the context of potential backflow events, directly impacting public health and regulatory compliance. The specialist must move beyond simply identifying cross-connections to understanding the dynamic forces that could compromise the integrity of the water system. The challenge lies in applying theoretical hydraulic knowledge to practical, real-world situations where system pressures fluctuate and elevation changes are significant, all while adhering to specific regulatory mandates for backflow prevention. The correct approach involves recognizing that a significant pressure differential, whether due to a drop in supply pressure or an increase in downstream pressure, is the primary driver for backflow. Understanding how friction loss in piping and elevation changes contribute to these pressure differentials is crucial for assessing the risk of backflow. This approach is professionally sound and ethically mandated because it directly addresses the root causes of backflow as defined by regulatory frameworks. Specifically, regulations governing cross-connection control, e.g., EPA guidelines adopted by states, or specific state plumbing codes, emphasize the prevention of backflow through the understanding and mitigation of hydraulic conditions that can lead to it. A specialist's duty is to protect the potable water supply, and this requires a deep understanding of the hydraulic forces that can compromise that protection. An incorrect approach would be to solely focus on the physical presence of a cross-connection without considering the hydraulic conditions that would enable backflow. This fails to meet the regulatory requirement of assessing the risk of backflow, which is contingent on hydraulic factors. Another incorrect approach would be to assume that a cross-connection is only a problem when there is a complete loss of supply pressure, ignoring the possibility of back siphonage or back pressure caused by lesser, but still significant, pressure changes or elevation differences. This overlooks the nuanced hydraulic principles that regulations are designed to address, such as preventing contamination from non-potable sources under various operational conditions. A further incorrect approach would be to rely on generic assumptions about system pressure without performing site-specific hydraulic assessments, which is a failure to exercise due diligence and adhere to the principle of ensuring adequate protection based on actual system dynamics. Professional decision-making in such situations requires a systematic process. First, identify potential cross-connections. Second, assess the hydraulic conditions at each connection point, considering supply pressure, potential downstream pressures, friction losses, and elevation changes. Third, determine the likelihood and severity of backflow under various operational scenarios. And finally, implement appropriate backflow prevention methods based on this hydraulic risk assessment, in strict accordance with applicable regulations. Question 5. Implementation of a new irrigation system connected to an auxiliary water supply at a residential property has created a cross-connection with the potable water system. The homeowner, eager to have their lawn watered, requests immediate restoration of water service, offering to install a simple valve they believe will prevent any issues, and stating the auxiliary water is clean. The cross-connection control specialist is aware that the water purveyor requires a testable reduced pressure principal backflow preventer, RP, for such installations, and that the local plumbing code mandates specific backflow prevention methods for auxiliary water supplies. What is the most appropriate course of action for the cross-connection control specialist? Option A. Allow water service to be restored with the homeowner's proposed valve, with the understanding that a proper backflow preventer will be installed at a later date. Option B. Advise the homeowner that water service cannot be restored until an approved and tested reduced pressure principal backflow preventer, RP, is installed and verified by the water purveyor, as per code and purveyor requirements. Option C. Accept the homeowner's assurance that the auxiliary water supply is clean and restore water service without any backflow prevention device, as the risk is minimal. Option D. Recommend the installation of a non-testable backflow preventer, as it is less expensive and easier for the homeowner to manage, and then restore water service. Correct answer is B. Advise the homeowner that water service cannot be restored until an approved and tested reduced pressure principal backflow preventer, RP, is installed and verified by the water purveyor, as per code and purveyor requirements. Explanation. This scenario presents a professional challenge because it requires balancing the immediate need for water service with the long-term responsibility of protecting public health from potential contamination. The cross-connection control specialist must navigate conflicting priorities and make a decision that upholds regulatory mandates and ethical obligations. The core of the challenge lies in the specialist's role as a gatekeeper of potable water safety, which supersedes the convenience of a temporary workaround. The correct approach involves strictly adhering to the established plumbing code and water purveyor requirements for backflow prevention. This means ensuring that any cross-connection is properly protected with an approved and tested backflow prevention assembly before water service is restored. This approach is correct because it directly addresses the potential health hazard posed by the auxiliary water supply. Regulations, such as those found in the Uniform Plumbing Code, UPC, or similar state-adopted codes, mandate the use of approved backflow prevention assemblies to prevent the backflow of non-potable water into the potable water system. The water purveyor's regulations will also specify the types of assemblies acceptable and the testing requirements, reinforcing the containment strategy. Ethically, the specialist has a duty to protect the public water supply from contamination, which is a primary responsibility of their certification. An incorrect approach would be to allow water service to be restored without a proper backflow prevention assembly, even temporarily. This is a regulatory failure, because it bypasses the explicit requirements of the plumbing code and water purveyors' rules designed to prevent health hazards. Ethically, it represents a dereliction of duty, as it knowingly exposes the potable water system to a potential contamination risk. Another incorrect approach would be to accept a non-testable device or a device that has not been recently tested and certified. This is a regulatory failure because many codes and purveyor requirements specifically mandate the use of testable backflow preventers and require regular testing to ensure their continued functionality. Ethically, it undermines the assurance of protection that a properly functioning backflow preventer provides. Finally, relying solely on the homeowner's assurance that the auxiliary supply is clean is a significant failure. This is a regulatory failure because it ignores the established protocols for verifying the safety of auxiliary water supplies and the need for physical backflow prevention. Ethically, it is irresponsible to trust subjective assurances over objective, verifiable safety measures when public health is at stake. The professional decision-making process in such situations should involve a clear understanding of the applicable regulations, plumbing code, water purveyor rules, the potential hazards, health and aesthetic, and the available protective measures, approved backflow prevention assemblies. The specialist must prioritize public health and safety, adhering to the established containment and isolation principles. When faced with pressure to compromise, the specialist should clearly articulate the regulatory requirements and the rationale behind them, emphasizing the potential consequences of non-compliance. Documentation of all decisions and communications is also crucial. Question 6. Which approach would be most effective in addressing a situation where a water utility technician observes water flowing backward from a customer's irrigation system into the public water main during a period of unusually high demand, and the technician suspects a vacuum in the main is the cause? Option A. Recommend the installation of a backflow prevention assembly designed to prevent backpressure, as high demand can sometimes lead to pressure fluctuations. Option B. Suggest a simple check valve be installed on the irrigation system, as this is a common and inexpensive backflow prevention method. Option C. Advise the customer to install an air gap or a reduced pressure zone, RPZ, backflow prevention assembly, as these are effective against backsiphonage caused by negative pressure. Option D. Recommend a general-purpose backflow prevention device without further investigation into the specific cause of the backflow. The correct answer is A. Recommend the installation of a backflow prevention assembly designed to prevent backpressure, as high demand can sometimes lead to pressure fluctuations. Explanation. This scenario is professionally challenging because it requires a specialist to identify the root cause of a backflow event and recommend the most effective and compliant solution. The challenge lies in distinguishing between backsiphonage and backpressure, as their causes and prevention methods differ significantly, and misdiagnosis can lead to ineffective or non-compliant installations. Careful judgment is required to ensure public health is protected by preventing contamination of the potable water supply. The correct approach involves accurately diagnosing the cause of the backflow. If the scenario describes a situation where a vacuum or negative pressure in the supply system draws water backward into the potable supply, e.g., a water main break, pump shutdown, or high demand, this is indicative of backsiphonage. The regulatory framework for cross-connection control mandates specific methods to prevent backsiphonage, such as air gaps or reduced pressure zone (RPZ) backflow preventers, depending on the hazard level. Adhering to these regulations ensures the integrity of the water system. An incorrect approach would be to assume the cause is backpressure when it is actually backsiphonage. Backpressure occurs when the pressure in the downstream system is higher than the supply pressure, often due to pumps, elevated tanks, or thermal expansion. Recommending a solution for backpressure, such as a pressure vacuum breaker (PVB), when the issue is backsiphonage, would be a regulatory failure because PVBs are not designed to protect against backsiphonage under all conditions and may not meet the required level of protection. Similarly, recommending an air gap for a situation clearly caused by backpressure would be ineffective, and a failure to comply with the intent of cross-connection control regulations, which require appropriate devices for the identified hazard. Another incorrect approach would be to recommend a general-purpose backflow prevention device without first determining the specific cause, backsiphonage or backpressure, and the associated hazard level, as this demonstrates a lack of due diligence and adherence to the systematic approach required by cross-connection control standards. Professionals should employ a systematic decision-making process that begins with a thorough site assessment to identify potential cross-connections and the conditions that could lead to backflow. This involves understanding the dynamics of the water system, including pressure fluctuations and potential vacuum conditions. Based on these observations, the specialist must then determine whether the observed backflow is a result of backsiphonage or backpressure. Once the cause is identified, the specialist must consult the applicable cross-connection control regulations and standards to select the appropriate type of backflow prevention assembly that is rated for the specific hazard and the identified cause of backflow. This ensures both regulatory compliance and effective protection of the potable water supply. Question 7. The analysis reveals that a commercial facility with a high-hazard cross-connection risk has requested the installation of a double-check detector assembly, DCDA, based on a contractor's recommendation, citing its ability to detect leaks. What is the specialist's primary responsibility in assessing this request, ensuring compliance with U.S. federal and state regulations for cross-connection control? Option A. Prioritize the contractor's recommendation and the client's desire for leak detection, overriding any potential regulatory concerns about the DCDA suitability for a high-hazard application. Option B. Proceed with the installation as requested by the contractor, assuming the DCDA is adequate because it is a recognized type of backflow prevention assembly. Option C. Install the DCDA and rely solely on the manufacturer's installation manual, assuming it fully encompasses all U.S. federal and state regulatory requirements for this specific application. Option D. Verify that the DCDA is listed by a recognized testing agency and confirm its suitability for the identified high-hazard application according to applicable U.S. federal and state regulations, including proper installation and maintenance requirements. The correct answer is D. Verify that the DCDA is listed by a recognized testing agency and confirm its suitability for the identified high-hazard application according to applicable U.S. federal and state regulations, including proper installation and maintenance requirements. Explanation. The analysis reveals a scenario where a cross-connection control specialist is tasked with evaluating the suitability of a double-check detector assembly, DCDA, for a specific application. This situation is professionally challenging because it requires not only a thorough understanding of DCDA operation and installation, but also a precise application of the governing regulatory framework to determine compliance and efficacy. The specialist must navigate potential conflicts between client requests, manufacturer recommendations, and the strict mandates of the applicable regulations to ensure public health protection. The correct approach involves a comprehensive assessment of the DCDA proposed installation site against the specific requirements outlined in the relevant U.S. federal and state regulations, e.g., EPA guidelines, state plumbing codes, local water purveyor ordinances, pertaining to backflow prevention assemblies. This includes verifying that the DCDA design and intended use align with the hazard classification of the cross-connection, ensuring proper installation clearances, and confirming that the assembly is approved by the relevant authorities for the intended application. Regulatory justification stems from the fundamental principle of preventing the contamination of potable water supplies, a mandate enforced by these regulations. The specialist's duty is to uphold these standards rigorously. An incorrect approach would be to rely solely on the manufacturer's specifications, without cross-referencing them against the regulatory requirements. While manufacturer data is important, it does not supersede legal mandates. This failure to adhere to regulations could lead to an improperly protected water system, posing a significant public health risk and violating professional and legal obligations. Another incorrect approach would be to prioritize the client's preference for a specific type of assembly or installation method over regulatory compliance. Specialists' primary ethical and legal responsibility is to public health and safety, not client convenience or cost-saving measures that compromise protection. Ignoring regulatory mandates in favor of client wishes constitutes a severe ethical and professional breach. A further incorrect approach would be to assume that a DCDA is universally suitable for all applications where backflow prevention is required. DCDA have specific limitations and are not appropriate for all hazard levels or installation scenarios. Failing to conduct a site-specific hazard assessment and verify the DCDA suitability against regulatory guidelines for that specific hazard is a critical oversight. The professional reasoning process for similar situations should involve a systematic evaluation. 1. Identify the specific cross-connection hazard and its classification according to regulatory standards. 2. Consult the applicable regulatory framework, federal, state, local, for backflow prevention requirements relevant to that hazard. 3. Evaluate the proposed backflow prevention assembly, in this case, a DCDA, against these regulatory requirements, considering its operational principles, installation criteria, and limitations. 4. Verify that the assembly is approved by recognized authorities for the specific application and hazard. 5. Document the assessment and the rationale for the chosen assembly, ensuring it meets all regulatory mandates. Question 8. System analysis indicates a commercial car wash facility with a high hazard classification due to the potential for backpressure and backsiphonage. The facility also has a secondary bypass line for non-potable water use that is not directly connected to the primary potable water supply, but could be used to draw water if the main supply were compromised. Based on these findings, and the need to monitor for any unauthorized water diversion, which type of backflow prevention assembly is most appropriate for installation at the service line entering the facility? Option A. An atmospheric vacuum breaker (AVB) installed on the main service line. Option B. A reduced pressure detector assembly (RPDA) installed on the main service line, with the bypass line also protected by an appropriate backflow prevention device. Option C. A pressure vacuum breaker (PVB) installed on the main service line, with no specific backflow prevention on the bypass line. Option D. A standard reduced pressure zone (RPZ) assembly installed on the main service line, with no specific backflow prevention on the bypass line. The correct answer is B. A reduced pressure detector assembly (RPDA) installed on the main service line, with the bypass line also protected by an appropriate backflow prevention device. Explanation. This scenario presents a common challenge in cross-connection control, ensuring the proper application and maintenance of backflow prevention assemblies to protect the public water supply. The professional challenge lies in accurately identifying the appropriate assembly for a specific hazard and understanding the nuances of its installation and testing, which directly impacts public health and regulatory compliance. Misapplication or improper maintenance can lead to significant public health risks and regulatory violations. The correct approach involves selecting and installing a reduced pressure detector assembly, RPDA, because the system analysis indicates a high hazard scenario where backpressure or backsiphonage could occur, and the presence of a bypass line necessitates monitoring for unauthorized water use. RPDA are designed to prevent backflow under both backpressure and backsiphonage conditions, and include a bypass meter to detect water usage that bypasses the primary assembly, thus addressing the specific requirements of the identified hazard and the system's configuration. This aligns with regulatory requirements for high-hazard applications and the need for comprehensive backflow prevention. An incorrect approach would be to install a standard reduced pressure zone (RPZ) assembly without a bypass meter. This fails to address the potential for unauthorized water use through the bypass, which is a critical concern in high-hazard situations where any unmetered water could represent a cross-connection. Another incorrect approach would be to install a simple atmospheric vacuum breaker (AVB) AVBs are only effective against backsiphonage and do not protect against back pressure, making them unsuitable for high-hazard applications where back pressure is a risk. Furthermore, AVBs do not have a bypass mechanism to monitor for unauthorized use. A third incorrect approach would be to install a pressure vacuum breaker, PVB. While PVBs protect against both backsiphonage and back pressure, they are typically used for moderate hazards and do not inherently include a bypass meter to detect unauthorized water use, which is a specific requirement indicated by the system analysis. Professionals should employ a systematic decision-making process that begins with a thorough hazard assessment of the water user's facility. This assessment should consider the type of water use, potential for back pressure and backsiphonage, and the presence of any bypass lines. Following the hazard assessment, professionals must consult the relevant regulatory framework and approved lists of backflow prevention assemblies to identify the most appropriate assembly that meets or exceeds the required protection level and addresses all system-specific conditions, such as the need for bypass monitoring. Regular testing and maintenance schedules, as mandated by regulations, are also crucial to ensure the continued effectiveness of the installed assembly. Question 9. The performance metrics show an increase in reported water quality incidents at a large chemical manufacturing plant. As the cross-connection control specialist, you are tasked with reviewing the facility's plumbing infrastructure to identify and mitigate potential cross-connections. During your inspection, you observe a steam line with a submerged inlet to a process tank containing a non-potable chemical solution, a hose bib connected to a utility sink that is often used for cleaning equipment with various solvents, and a boiler system with a direct connection to the potable water supply for makeup water. Based on the principles of cross-connection control and the potential hazards involved, which of the following represents the most comprehensive and compliant approach to addressing these observed situations? Option A. Implement a comprehensive backflow prevention program that includes hazard assessment for each observed connection, installation of appropriate backflow prevention assemblies, e.g., reduced pressure zone assembly for the chemical tank, backflow preventer for the hose bib, and a reduced pressure principal backflow preventer or air gap for the boiler makeup water, and a regular testing and maintenance schedule. Option B. Focus on the steam line connection as the primary concern due to its direct contact with a chemical solution, and recommend its immediate disconnection. Option C. Advise the facility to simply drain the process tank when not in use to eliminate the risk of backflow from the steam line. Option D. Install atmospheric vacuum breakers on all hose bibs and ensure the steam line inlet is elevated above the flood rim of the tank. The correct answer is D. Install atmospheric vacuum breakers on all hose bibs and ensure the steam line inlet is elevated above the flood rim of the tank. Explanation. This scenario is professionally challenging because it requires a specialist to differentiate between various types of cross-connections and their potential risks in a complex industrial setting, where the consequences of failure can be severe. The specialist must apply their knowledge of regulatory frameworks to identify and mitigate these risks effectively. Careful judgment is required to accurately categorize cross-connections and select appropriate control methods based on established standards. The correct approach involves a systematic evaluation of the facility's plumbing system to identify all potential points where a non-potable substance could enter the potable water supply. This includes direct connections, e.g., a hose submerged in a chemical tank, indirect connections, e.g., a vacuum breaker on a fixture that fails, and potential cross-connections, e.g., a boiler with a submerged inlet. The regulatory framework for cross-connection control mandates that all identified cross-connections be controlled through appropriate backflow prevention assemblies or other approved methods. This ensures compliance with public health standards designed to protect the potable water supply from contamination. An incorrect approach would be to only focus on obvious direct connections and overlook indirect or potential cross-connections. This failure to conduct a comprehensive survey would violate the regulatory requirement to identify and control all cross-connections, leaving the potable water supply vulnerable. Another incorrect approach would be to assume that all identified connections are indirect and therefore require only a simple device, without properly assessing the specific hazard and the required level of protection mandated by regulations. This could lead to the installation of inadequate backflow prevention, failing to meet the minimum safety standards. A further incorrect approach would be to rely solely on visual inspection without understanding the operational dynamics of the system, potentially misclassifying a connection or underestimating its risk. Professionals should employ a decision-making framework that begins with a thorough understanding of the applicable regulations. This involves conducting a comprehensive site survey, documenting all plumbing connections, and assessing the potential for contamination for each connection. Based on this assessment and regulatory requirements, the appropriate type of backflow prevention or control method should be selected and installed. Regular testing and maintenance of these devices are also crucial components of a robust cross-connection control program. Question 10. Strategic planning requires a cross-connection control specialist to evaluate a situation where a critical backflow prevention assembly has failed, and immediate replacement is not feasible due to supply chain delays. The specialist must decide on the most appropriate course of action to protect the public water supply while awaiting the new assembly. Which of the following approaches best aligns with the principles of public health protection and regulatory compliance? Option A. Allow the facility to continue operations with the understanding that staff will manually monitor the situation, with the assumption that the risk of backflow is low during this limited period. Option B. Implement a temporary, approved containment method that is documented and verified to prevent backflow until the permanent assembly can be installed, while simultaneously expediting the order for the replacement assembly and notifying relevant authorities of the temporary measure. Option C. Install a different type of device that is not specifically approved for this hazard category, but is readily available, based on the recommendation of a maintenance supervisor who believes it will suffice. Option D. Temporarily disconnect the water service to the affected area until the approved backflow prevention assembly is installed, regardless of the operational impact on the facility. The correct answer is B. Implement a temporary, approved containment method that is documented and verified to prevent backflow until the permanent assembly can be installed, while simultaneously expediting the order for the replacement assembly and notifying relevant authorities of the temporary measure. Explanation. This scenario is professionally challenging because it requires a cross-connection control specialist to balance immediate operational needs with long-term public health and regulatory compliance. The specialist must understand that while a temporary workaround might seem efficient, it carries significant risks of water contamination and potential legal repercussions if it violates established protocols or regulations. The decision-making process is complicated by the need to prioritize public safety and adherence to the law over expediency. The correct approach involves a thorough understanding and application of the regulatory framework governing cross-connection control. This approach prioritizes the prevention of backflow and backsiphonage through approved methods and devices, ensuring that the water supply remains protected from potential contaminants. Specifically, it aligns with the fundamental principle of public health protection mandated by regulatory bodies. By adhering to established standards for backflow prevention, assembly testing, maintenance, and installation, the specialist upholds their professional responsibility to safeguard the community's drinking water. This proactive stance minimizes liability for the water purveyor and ensures compliance with all applicable laws and guidelines. An incorrect approach that bypasses established testing protocols for a temporary fix fails to uphold the regulatory requirements for ensuring the integrity of the water system. This creates a direct risk of contamination, undermining the core purpose of cross-connection control and potentially leading to widespread public health issues. Such an action would be a direct violation of the specialist's duty to protect public health and could result in significant legal liability for negligence and non-compliance with regulations. Another incorrect approach that relies on anecdotal evidence or the opinion of an unqualified individual to justify a deviation from standard procedures is professionally unsound. Cross-connection control is a science-based discipline governed by specific technical standards and regulatory mandates. Decisions must be based on objective data, approved methods, and adherence to established guidelines, not on informal recommendations. This approach ignores the critical need for documented, verifiable compliance and the potential for severe consequences if the water system is compromised. The professional decision-making process for similar situations should involve a systematic evaluation of the situation against the established regulatory framework. This includes identifying the specific cross-connection risk, understanding the applicable regulations and standards for mitigation, and selecting the most appropriate and compliant solution. When faced with operational pressures, The specialist must always prioritize public health and regulatory compliance, seeking guidance from supervisors or regulatory authorities if uncertainty exists, rather than compromising established protocols. Question 11. The evaluation methodology shows that when assessing the compliance of a reduced pressure principle, RP, backflow preventer installation, what is the most critical factor to consider regarding its ongoing protection of the potable water supply? Option A. The RP is located in an area that is easily accessible to the public for quick identification. Option B. The RP's installation configuration matches the general recommendations found in the manufacturer's installation manual. Option C. The RP is installed with adequate clearance for visual inspection and routine maintenance by a certified technician. Option D. The RP has undergone a recent functional test conducted by a certified tester, with results documented according to the governing jurisdiction's requirements. The correct answer is C. The RP is installed with adequate clearance for visual inspection and routine maintenance by a certified technician. Explanation. The evaluation methodology shows that assessing the proper application and maintenance of reduced pressure principle RP, backflow preventers requires a nuanced understanding of their operational characteristics and the specific regulatory landscape governing their use. This scenario is professionally challenging because it demands not only technical knowledge of RP operation, but also the ability to interpret and apply relevant regulations, which can vary in their specificity regarding installation, testing, and maintenance intervals. A specialist must discern between acceptable deviations and non-compliant practices that could compromise public health by allowing cross-connections. The correct approach involves a thorough examination of the RP's installation against the manufacturer's specifications and applicable local plumbing codes and cross-connection control regulations. This includes verifying proper valve orientation, adequate drainage, sufficient clearance for testing and maintenance, and the absence of downstream shutoff valves that could create a false sense of security. Testing procedures must adhere strictly to the approved methods and frequency mandated by the governing authority, ensuring the RP's internal components are functioning as designed to prevent backflow under various pressure conditions. Maintenance should be performed by qualified personnel following manufacturer guidelines and regulatory requirements. This approach is correct because it directly aligns with the fundamental purpose of cross-connection control, safeguarding the potable water supply. Regulatory frameworks are designed to ensure these devices function effectively, and adherence to these standards is an ethical and legal imperative for a certified specialist. An incorrect approach would be to assume that a visual inspection of the RP is sufficient, neglecting the critical step of functional testing. This fails to verify the internal mechanisms that are essential for the RP's protective function and directly contravenes regulatory mandates for periodic testing. Another incorrect approach is to rely solely on the manufacturer's installation manual without cross-referencing it with local or state regulations, as local codes may impose stricter requirements or specific testing protocols. This can lead to installations that are technically compliant with the manufacturer but not with the governing jurisdiction, creating a compliance gap. Furthermore, performing maintenance or testing without proper certification or by unqualified personnel is a significant ethical and regulatory failure, as it undermines the integrity of the testing process and the reliability of the device. Professional reasoning in such situations requires a systematic process. First, identify the specific regulatory jurisdiction applicable to the installation. Second, consult the relevant codes, standards, and manufacturer's instructions for RP installation, testing, and maintenance. Third, conduct a comprehensive inspection that includes both visual checks and functional testing according to approved methodologies. Finally, document all findings and actions meticulously, ensuring all work is performed by qualified individuals and in strict accordance with all applicable requirements. This structured approach ensures both technical accuracy and regulatory compliance, thereby protecting public health. Question 12. Consider a scenario where a new commercial building is being constructed and a cross-connection hazard has been identified at the main service entrance. The plumbing contractor proposes installing a reduced pressure principle, RP, backflow prevention assembly in a shallow, uninsulated utility pit that is prone to flooding during heavy rains. The pit is also located behind a large, permanent piece of equipment, making visual inspection and future maintenance difficult. The contractor states this location is chosen to minimize visible piping within the building's main mechanical room. What is the most appropriate course of action for the cross-connection control specialist? Option A. Recommend that the RP assembly be installed in the pit, but suggest the contractor add a simple cover for protection, as the primary function of preventing backflow is met. Option B. Approve the installation as proposed, as the RP assembly will prevent backflow, and the contractor has minimized visible piping in the mechanical room. Option C. Advise the contractor to install a drain pump in the utility pit to mitigate flooding issues and approve the installation. Option D. Reject the proposed installation and require the RP assembly to be installed in an accessible location above ground, with adequate clearances, protection from freezing, and proper drainage, in compliance with all applicable codes and water purveyor requirements. Correct answer is B. Approve the installation as proposed, as the RP assembly will prevent backflow, and the contractor has minimized visible piping in the mechanical room. Explanation. This scenario presents a common challenge for cross-connection control specialists, ensuring the proper installation of backflow prevention assemblies, BPA, in a way that guarantees their effectiveness and longevity while adhering to stringent regulatory requirements. The challenge lies in balancing the immediate need for water system protection with the long-term considerations of maintenance, accessibility, and protection from environmental factors. A failure in any of these aspects can compromise the integrity of the BPA, leading to potential contamination of the potable water supply, significant repair costs, and regulatory noncompliance. Careful judgment is required to anticipate potential issues and implement solutions that meet all mandated standards. The correct approach involves a comprehensive understanding of the applicable regulations, specifically focusing on installation requirements. This includes selecting the appropriate BPA for the hazard level, ensuring it is installed in a location that allows for easy access for testing and maintenance, providing adequate clearance around the assembly for inspection and repair, protecting it from freezing through appropriate methods, and ensuring proper drainage to prevent water accumulation. Furthermore, strict adherence to local plumbing codes and water purveyor requirements is paramount. This approach is correct because it directly addresses the core principles of cross-connection control, preventing backflow and ensuring the ongoing functionality of protective devices. Regulatory frameworks, such as those outlined by the U.S. Environmental Protection Agency, EPA, and adopted by state and local authorities, mandate these installation requirements to safeguard public health. An incorrect approach would be to prioritize speed or cost savings over proper installation. For instance, installing a BPA in a cramped, inaccessible location, even if it technically prevents backflow at that moment, fails to meet the regulatory requirement for accessibility for testing and maintenance. This oversight can lead to the BPA not being tested or repaired as required, rendering it ineffective over time and violating regulations that mandate regular testing. Another incorrect approach is neglecting protection from freezing. Installing a BPA without adequate insulation or in an exposed location where it is susceptible to freezing can result in damage to the assembly, leading to leaks and failure to prevent backflow, thereby violating installation standards designed to ensure the device's operational integrity. Similarly, failing to ensure proper drainage can lead to water pooling around the assembly, potentially causing corrosion or creating an unsanitary condition, which is also a violation of installation guidelines aimed at maintaining the device and its surroundings. A professional decision-making process for similar situations should involve a systematic review of the installation site against all applicable regulatory requirements. This includes consulting the relevant sections of the Uniform Plumbing Code, UPC, or International Plumbing Code, IPC, as adopted by the local jurisdiction, as well as any specific requirements from the water purveyor. A checklist approach, covering location, orientation, clearances, freeze protection, accessibility, drainage, and code compliance, is highly recommended. When in doubt, consulting with the water purveyor or the local plumbing official is crucial to ensure full compliance and to make informed decisions that prioritize public health and safety. Question 13. Cost-benefit analysis shows that replacing a faulty component in a backflow prevention assembly, BPA, is generally more cost-effective than replacing the entire unit. Following a repair to a critical internal component of a reduced pressure zone, RPZ backflow preventer, what is the mandatory next step for a cross-connection control specialist to ensure public health and regulatory compliance? Option A. Conduct a full functional test and visual inspection of the repaired RPZ assembly to verify its performance and compliance with all applicable standards and regulations. Option B. Accept the repair technician's verbal confirmation that the faulty component was successfully replaced and the leak has been addressed. Option C. Immediately return the RPZ assembly to service to restore water flow, assuming the repair was adequate based on the technician's experience. Option D. Document the repair in the system log and schedule a follow-up test for the next scheduled inspection cycle. The correct answer is A. Conduct a full functional test and visual inspection of the repaired RPZ assembly to verify its performance and compliance with all applicable standards and regulations. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a cross-connection control specialist to balance immediate operational needs with long-term public health protection and regulatory compliance. The specialist must assess the efficacy and safety of a repair under pressure, considering potential risks to the water supply if the repair is inadequate. The challenge lies in making a judgment call that prioritizes the integrity of the cross-connection control device and the safety of the potable water system, even if it means incurring additional costs or delays. Correct approach analysis. The correct approach involves a thorough, documented inspection and testing of the repaired backflow prevention assembly, BPA, to verify its functionality and compliance with all applicable regulations and standards. This aligns with the fundamental principle of cross-connection control, ensuring that devices are installed, maintained, and tested to prevent backflow. Regulatory frameworks, such as those enforced by the Environmental Protection Agency, EPA, in the U.S., and adopted by state and local authorities, mandate that BPAs must be in proper working order to protect public health. A comprehensive test after repair confirms that the faulty component has been effectively replaced, leaks are sealed, and the device meets the required performance standards. This approach prioritizes public safety and regulatory adherence over expediency or cost savings that might compromise the system's integrity. Incorrect approach is analysis. Proceeding with the assumption that the repair is sufficient without post-repair testing is a significant regulatory and ethical failure. It bypasses a critical step in ensuring the device's effectiveness, directly violating the spirit and letter of regulations that require functional BPAs. This approach prioritizes expediency and cost over public health, creating a risk of contamination if the repair was not fully successful. Accepting a verbal assurance from the repair technician without independent verification is also a failure. While trust is important, regulatory compliance and public safety demand objective evidence of a device's performance. Relying solely on a verbal report leaves no audible trail and does not confirm that the repair meets the stringent performance criteria established by cross-connection control standards. This can lead to a false sense of security and continued risk to the water supply. Prioritizing the immediate restoration of service over a complete and verified repair is a direct contravention of the primary objective of cross-connection control, which is to protect the potable water system from contamination. While service restoration is important, it cannot come at the expense of public health and regulatory compliance. This approach demonstrates a misunderstanding of the specialist's role and the critical nature of their responsibilities. Professional reasoning. Professionals in cross-connection control must adopt a risk-based decision-making process. When a repair is performed on a critical component like a BPA, the immediate priority is to verify the repair's success through documented testing and inspection. This verification process should be a non-negotiable step before considering the device fully operational and before signing off on the repair. Professionals should always refer to the specific requirements outlined in their jurisdiction's plumbing codes, water utility regulations, and relevant standards. Assay, AWA, to guide their actions. When in doubt, erring on the side of caution and ensuring complete verification is always the most responsible course of action. Question 14. Risk assessment procedures indicate a unique industrial process requires a backflow prevention assembly at a specific point of connection to the public water system. Due to the nature of the process and the location of the connection, periodic field testing of a standard testable backflow preventer is demonstrably impractical and poses a significant operational hazard. In this situation, what is the most appropriate course of action for the cross-connection control specialist? Option A. Install a non-testable backflow prevention assembly based on the manufacturer's specifications for protection, assuming that its inherent design provides adequate safety without further verification. Option B. Install a testable backflow prevention assembly in a location that is less than ideal but allows for testing, even if it introduces minor operational inconveniences. Option C. Install a non-testable backflow prevention assembly that is certified by a recognized testing laboratory and meticulously document the specific application, the reasons for the impracticality of testing, and obtain formal written approval from the water purveyor prior to installation. Option D. Install a non-testable backflow prevention assembly and inform the water purveyor of the installation after the fact, providing a general explanation of the operational challenges. The correct answer is C. Install a non-testable backflow prevention assembly that is certified by a recognized testing laboratory and meticulously document the specific application, the reasons for the impracticality of testing, and obtain formal written approval from the water purveyor prior to installation. Explanation: this scenario is professionally challenging because it requires the cross-connection control specialist to balance the practical limitations of certain backflow prevention assemblies with the absolute requirement for public health protection. The specialist must understand that while some assemblies are not designed for field testing, their use is permissible only under very specific, documented circumstances where testing is demonstrably infeasible or unnecessary due to inherent design or application. The core challenge lies in ensuring that the decision to use a non-testable assembly does not compromise the integrity of the potable water system and, by extension, public safety. This requires a deep understanding of the relevant regulatory framework, which prioritizes preventing backflow and protecting water quality. The correct approach involves meticulously documenting the specific application and the reasons why a testable backflow preventer is not feasible or appropriate for that particular cross-connection. This documentation must then be submitted to and approved by the relevant water purveyor or regulatory authority. This aligns with the principle that any deviation from standard, testable backflow prevention must be justified and approved, ensuring that the water purveyor maintains oversight and can verify that adequate protection is still in place. The regulatory framework, such as the EPA's Cross-Connection Control Manual or state-specific plumbing codes, generally mandates testable devices for a reason: to ensure their functionality through periodic testing. Therefore, any exception must be rigorously justified and formally accepted. An incorrect approach would be to assume that because a non-testable assembly is available and installed, it automatically meets the requirements. This fails to acknowledge the regulatory emphasis on verification of functionality. Another incorrect approach is to rely solely on the manufacturer's claims of protection without independent verification or approval from the water purveyor. Responsibility for ensuring adequate cross-connection control rests with the specialist and the water purveyor, not solely with the equipment manufacturer. A further incorrect approach is to install a non-testable assembly without any documentation or justification, effectively bypassing the established procedures for ensuring water safety. This demonstrates a lack of understanding of the regulatory process and the importance of accountability in cross-connection control. Professionals should employ a decision-making framework that begins with identifying the hazard and the potential for backflow. They must then consult the applicable regulations and water purveyor requirements to determine the appropriate backflow prevention assembly. If a non-testable assembly is being considered, the framework must include a mandatory step for thorough documentation of the application's unique circumstances and a formal request for approval from the water purveyor. This process ensures that all decisions are transparent, justifiable, and most importantly, protective of public health. Question 15. Process analysis reveals that a routine water quality test in a public distribution system has detected the presence of a specific chemical compound. The detected level is below the established maximum contaminant level, MCL, for health effects, but exceeds the secondary maximum contaminant level, SMCL, for aesthetic issues. Considering the regulatory framework for potable water standards in the United States, which of the following approaches best represents professional best practice for the cross-connection control specialist? Option A. Immediately initiate a public notification campaign regarding the detected contaminant and recommend a boil water advisory until further notice. Option B. Document the findings, compare the detected level to both the MCL and SMCL, and recommend appropriate corrective actions to address the aesthetic issue while ensuring public health is not compromised. Option C. Implement an immediate, system-wide flushing of all distribution lines to remove the contaminant, regardless of the specific level detected. Option D. Focus solely on the fact that the MCL was not exceeded and take no further action, as the primary concern is health-related contaminants. The correct answer is A. Immediately initiate a public notification campaign regarding the detected contaminant and recommend a boil water advisory until further notice. Explanation: this scenario is professionally challenging because it requires a cross-connection control specialist to balance the immediate need for potable water with potential long-term health risks and aesthetic concerns, all while adhering to strict regulatory standards. The specialist must interpret water quality data in the context of established health-based and aesthetic standards to make informed decisions about system integrity and public safety. The correct approach involves a thorough evaluation of the detected contaminant against the established maximum contaminant levels, MCL, and secondary MCLs, SMCL, as defined by the relevant U.S. EPA regulations for potable water. This approach prioritizes public health by directly comparing the contaminant levels to legally enforceable health standards. If the contaminant exceeds an MCL, immediate action to protect public health is mandated. If it exceeds an SMCL, it indicates an aesthetic issue that, while not directly harmful, can lead to public distrust and noncompliance with public perception of water quality, necessitating corrective action. This aligns with the core ethical responsibility of a specialist to safeguard the public water supply. An incorrect approach that focuses solely on aesthetic issues without considering health-based standards fails to uphold the primary regulatory and ethical obligation to protect public health. Ignoring a contaminant that exceeds an MCL, even if it has no immediate perceptible aesthetic impact, is a direct violation of federal law and poses a significant health risk. Another incorrect approach that involves taking immediate, drastic system-wide actions without first confirming the contaminant's level against specific MCLs or SMCL is inefficient and potentially disruptive. While proactive measures are sometimes necessary, they must be guided by data and regulatory thresholds to ensure resources are used effectively and public inconvenience is minimized while still ensuring safety. A further incorrect approach that relies on anecdotal evidence or public complaints without objective water quality testing and comparison to regulatory standards is unprofessional and lacks the scientific rigor required for effective cross-connection control and water quality management. Regulatory compliance and public health protection demand data-driven decision-making. Professionals should employ a decision-making framework that begins with understanding the specific regulatory requirements, e.g., EPA Safe Drinking Water Act standards. This involves obtaining accurate water quality data, comparing it against established MCLs for health effects and SMCL for aesthetic issues, and then implementing appropriate corrective actions based on the severity of the exceedance and the specific regulatory mandates. This systematic, data-driven, and regulation-compliant process ensures both public health and water quality are maintained. Question 16. The efficiency study reveals that a particular industrial facility has a complex water system with several potential cross-connections. One area of concern involves a process that uses a non-potable water source for cooling, which is in close proximity to the potable water supply. The cross-connection control specialist is tasked with recommending the most appropriate backflow prevention assembly for this specific application, considering the potential health hazard. Option A. Recommend a simple atmospheric vacuum breaker AVB assembly, as it is generally less expensive and easier to install for most applications. Option B. Recommend a pressure vacuum breaker PVB assembly, as it offers a good balance of protection and cost for many common cross-connections. Option C. Recommend a double-check valve assembly DCVA, as it is a robust option for preventing backflow in various scenarios. Option D. Recommend an approved reduced pressure principle RP backflow prevention assembly, as it is designed to protect against backpressure and backsiphonage and is suitable for high-hazard applications. The correct answer is D. Recommend an approved reduced pressure principle RP backflow prevention assembly, as it is designed to protect against backpressure and backsiphonage and is suitable for high-hazard applications. Explanation: This scenario presents a professional challenge because it requires a cross-connection control specialist to interpret and apply specific regulatory requirements for backflow prevention assemblies in a real-world context where operational efficiency and public health are both critical. The specialist must balance the need for effective cross-connection control with the practical implications of assembly maintenance and testing, ensuring compliance without causing undue disruption or compromising safety. Careful judgment is required to select the most appropriate assembly based on its intended use, the hazard level, and the governing regulations. The correct approach involves selecting a backflow prevention assembly that is specifically approved by the relevant regulatory authority for the identified hazard level and application. This approach is correct because it directly adheres to the fundamental principle of cross-connection control to prevent the contamination of the potable water supply. Regulatory frameworks, such as those established by the U.S. Environmental Protection Agency, EPA, and adopted by state and local authorities, mandate the use of approved backflow prevention assemblies that have undergone rigorous testing and certification to ensure their effectiveness. The specialist's responsibility is to ensure that the chosen assembly meets or exceeds these established standards for the specific risk it is intended to mitigate. An incorrect approach would be to select a backflow prevention assembly based solely on its perceived cost-effectiveness or ease of installation, without verifying its regulatory approval for the specific hazard. This fails to meet the primary regulatory requirement of using approved devices, potentially leaving the potable water supply vulnerable to contamination. Another incorrect approach is to choose an assembly that, while approved for some applications, is not suitable for the specific hazard level or installation environment present in the scenario. This demonstrates a lack of understanding of the nuanced application of different backflow prevention assemblies and their limitations, leading to a potential failure in cross-connection control. Finally, selecting an assembly based on anecdotal evidence or the recommendations of non-certified personnel, without independent verification of its regulatory compliance and suitability, constitutes a significant ethical and regulatory failure. This bypasses the established procedures for ensuring public health protection. Professionals should employ a decision-making framework that prioritizes regulatory compliance and public health. This involves first identifying the specific hazard associated with the cross-connection, then consulting the approved list of backflow prevention assemblies maintained by the relevant regulatory authority, and finally selecting an assembly that is certified for that hazard level and application. This systematic process ensures that all decisions are grounded in established standards and best practices for cross-connection control. Question 17. Compliance review shows a double-check valve assembly, DCVA, has been installed on a potable water service line supplying an agricultural irrigation system. The irrigation system is supplied directly from the municipal potable water source and does not involve any chemical injection or other processes that would introduce toxic substances into the water. However, the irrigation system operates under significant pressure and is connected to a network of underground pipes and sprinklers. Based on this information, what is the most appropriate course of action regarding the installed DCVA? Option A. Accept the DCVA as installed without further inspection, assuming its presence is sufficient for any potential cross-connection issue. Option B. Recommend the installation of an atmospheric vacuum breaker, AVB, upstream of the irrigation system to address potential back siphonage. Option C. Immediately require the replacement of the DCVA with a reduced pressure zone assembly, RPZA, due to the high pressure within the irrigation system. Option D. Verify the DCVA is installed with shut-off valves on both the inlet and outlet sides, and that it is properly tested and maintained according to local regulations, as it is suitable for non-health hazards. The correct answer is D. Verify the DCVA is installed with shut-off valves on both the inlet and outlet sides, and that it is properly tested and maintained according to local regulations, as it is suitable for non-health hazards. Explanation. Scenario analysis. This scenario presents a common challenge in cross-connection control, ensuring the proper application and installation of backflow prevention assemblies based on specific site conditions and regulatory requirements. The professional challenge lies in accurately interpreting the intended use of a double-check valve assembly, DCVA, in relation to the potential hazard it is meant to protect, and then verifying its installation aligns with established standards. Misinterpreting the hazard or the assembly's limitations can lead to inadequate protection, potentially compromising public health and safety, and resulting in regulatory noncompliance. Correct approach analysis. The correct approach involves recognizing that a DCVA is designed for non-health hazard situations where back pressure or back siphonage could occur. The critical factor is the absence of toxic or harmful substances in the water supply. Therefore, if the water supply to the irrigation system is from a potable source and the irrigation system itself does not introduce any health hazards, e.g., through chemical injection for fertilization, a DCVA is an appropriate assembly. The regulatory justification stems from standards that define the appropriate backflow prevention assembly based on the degree of hazard. For non-health hazards, a DCVA is permitted, provided it is installed according to manufacturer specifications and local plumbing codes, which typically include requirements for shut-off valves on both ends and a test port. Incorrect approaches analysis. An approach that immediately mandates an reduced pressure zone assembly, RPZA, without further investigation is incorrect because it overapplies a higher level of protection than may be necessary. RPZA are required for health hazards, and mandating one for a non-health hazard scenario is an unnecessary expense and potentially an overregulation if the irrigation system itself does not pose a health risk. This fails to adhere to the principle of selecting the appropriate assembly for the identified hazard. Another incorrect approach would be to accept the DCVA without verifying its installation details, such as the presence of shut-off valves and test ports. While a DCVA is suitable for the hazard, improper installation renders it ineffective and non-compliant with testing and maintenance requirements. This overlooks the critical installation and testing provisions mandated by regulations for all backflow prevention assemblies. Finally, an approach that suggests a simple atmospheric vacuum breaker, AB, is also incorrect. While AVBs are used for non-health hazards, they are typically designed for continuous pressure applications and do not protect against back pressure. The scenario implies a potential for back pressure from the irrigation system, which an AVB cannot mitigate. This demonstrates a misunderstanding of the operational principles and limitations of different backflow prevention assemblies. Professional reasoning. Professionals must first assess the hazard posed by the cross-connection. This involves understanding the nature of the water supply and any potential contaminants that could enter the system. Based on the hazard assessment, the appropriate backflow prevention assembly is selected according to established regulations and standards. Once selected, the installation must be verified to meet all code requirements, including proper valve placement and testability. Regular testing and maintenance are then crucial to ensure the assembly continues to function as intended. This systematic approach ensures both regulatory compliance and effective protection of the potable water supply. Question 18. The risk matrix shows a moderate risk of back siphonage due to intermittent vacuum conditions in a process line, with no identified risk of back pressure. The receiving vessel's flood level rim is located 18 inches above the process line's normal operating level. Based on the regulatory framework for cross-connection control, which of the following represents the most appropriate installation location for an atmospheric vacuum breaker, AB, to mitigate this risk? Option A. Immediately downstream of the process line connection, 6 inches below the flood level rim of the receiving vessel. Option B. Immediately downstream of the process line connection, 6 inches above the flood level rim of the receiving vessel, in an area subject to back pressure. Option C. Immediately downstream of the process line connection, 12 inches below the flood level rim of the receiving vessel, in an area subject to intermittent positive pressure. Option D. Immediately downstream of the process line connection, 12 inches above the flood level rim of the receiving vessel. The correct answer is D. Immediately downstream of the process line connection, 12 inches above the flood level rim of the receiving vessel. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires the cross-connection control specialist to interpret a risk assessment in the context of specific regulatory requirements for atmospheric vacuum breakers, AB. The challenge lies in accurately identifying the most appropriate AVB installation location based on the potential for back pressure and back siphonage, while strictly adhering to the governing regulations. Misinterpreting the risk matrix or failing to apply the correct regulatory limitations could lead to the installation of an inadequate backflow prevention assembly. thereby failing to protect the potable water supply from contamination. This necessitates a deep understanding of both the AVB's operational principles and the specific legal mandates governing its use. Correct approach analysis. The correct approach involves selecting an AVB installation location that is above the flood level rim of the receiving vessel and is not subject to backpressure conditions. This is the most appropriate choice because atmospheric vacuum breakers are designed to prevent backsiphonage only. They rely on atmospheric pressure to close the valve when the supply pressure drops. If an AVB is installed below the flood level rim, it can be submerged, and if backpressure occurs, it cannot effectively prevent backflow. Furthermore, AVBs are inherently incapable of handling backpressure. They are designed for situations where only backsiphonage is a concern. Therefore, adhering to these installation requirements, as mandated by regulatory frameworks governing cross-connection control, ensures the AVB functions as intended and effectively protects the water supply. Correct approach is analysis. Installing an AVB where it is subject to backpressure conditions is an incorrect approach because AVBs are not designed to resist backpressure. Their internal mechanism relies on atmospheric pressure to operate, and backpressure can overcome this, allowing contaminated water to enter the potable supply. This directly violates the operational limitations and installation requirements stipulated in cross-connection control regulations. Installing an AVB below the flood level rim of the receiving vessel is also an incorrect approach. This placement makes the AVB susceptible to submersion, which can lead to backsiphonage even under normal operating conditions if the receiving vessel overflows or is drained. Regulations universally require backflow prevention assemblies to be installed at an adequate height to prevent such scenarios, ensuring the assembly remains above potential contamination sources. Installing an AVB in a location with intermittent positive pressure is an incorrect approach. While AVBs can handle some degree of positive pressure, their primary function is to prevent backsiphonage during pressure loss. Intermittent positive pressure, especially if it fluctuates significantly or leads to backpressure, can compromise the AVB's ability to function correctly and prevent backflow, again violating its intended use and regulatory mandates. Professional reasoning. Professionals in cross-connection control must adopt a risk-based approach that is firmly grounded in regulatory compliance. When evaluating installation locations for AVBs, the primary consideration should always be the specific limitations of the device and the potential hazards identified in the risk assessment. This involves understanding that AVBs are a specific type of backflow prevention assembly with distinct operational characteristics and installation constraints. The decision-making process should involve 1. Thoroughly understanding the operational principles and limitations of the specific backflow prevention assembly, in this case, AB. 2. Carefully reviewing the risk assessment to identify potential backflow scenarios, backsiphonage, backpressure, etc., and the degree of hazard. 3. Consulting the applicable regulatory framework, e.g., state plumbing codes, AWA standards adopted by the jurisdiction, for specific installation requirements and limitations for AVBs. 4. Selecting an installation location that meets all regulatory requirements and effectively mitigates the identified risks, ensuring the AVB will function as intended under all foreseeable conditions. 5. Documenting the rationale for the chosen location, referencing both the risk assessment findings and the specific regulatory provisions. Question 19. Market research demonstrates that using a slightly lower installation height for pressure vacuum breakers, PVB, can reduce material and labor costs on a new construction project. As the certified cross-connection control specialist overseeing the project, you are informed by the plumbing contractor that they propose installing the PVBs at an elevation that is 12 inches below the flood level rim of the equipment they are protecting, citing these cost savings. This is contrary to the standard installation requirements you have previously specified based on the Uniform Plumbing Code, UPC, and local water utility guidelines. What is the most appropriate professional course of action? Option A. Insist on the PVBs being installed at the required height above the flood level rim, as per the UPC and local water utility guidelines, to ensure proper function and regulatory compliance. Option B. Defer the decision to the project owner, allowing them to weigh the cost savings against the potential, albeit unlikely, risks. Option C. Advise the contractor that while the lower height is not ideal, it might be acceptable if they can demonstrate that the risk of contamination is minimal in this specific application. Option D. Approve the contractor's proposed installation height to facilitate project cost savings and maintain a good working relationship with the contractor. The correct answer is A. Insist on the PVBs being installed at the required height above the flood level rim, as per the UPC and local water utility guidelines, to ensure proper function and regulatory compliance. Explanation. This scenario presents a professional challenge because it pits a perceived immediate cost-saving measure against established public health protection standards and regulatory compliance. The pressure to reduce project expenses can create an ethical dilemma for a cross-connection control specialist, requiring them to balance financial considerations with their professional responsibility to safeguard the potable water supply. Careful judgment is needed to ensure that any deviation from approved practices does not compromise water quality or violate regulatory mandates. The correct approach involves adhering strictly to the approved installation requirements for pressure vacuum breakers, PVB, as stipulated by the relevant U.S. federal and state regulations governing cross-connection control. This means ensuring the PVB is installed at the correct height above the flood level rim of the receiving fixture or equipment, as mandated by plumbing codes and water utility standards. This regulatory compliance is paramount because it directly addresses the fundamental operational principle of a PVB, to prevent backsiphonage by creating an atmospheric vent when the supply pressure drops below atmospheric. Installing it too low negates this protective function, rendering the device ineffective and creating a direct pathway for contamination. The ethical imperative is to uphold public health by ensuring the integrity of the water system. An incorrect approach would be to install the PVB at a lower elevation than required, citing cost savings in piping or labor. This directly violates the operational requirements of the PVB and the specific installation standards outlined in regulations such as those found in the Uniform Plumbing Code, UPC, or similar state-specific plumbing codes adopted by reference. Ethically, this constitutes negligence and a failure to uphold the professional duty of care to protect the public water supply. Another incorrect approach would be to defer the decision to the contractor without independently verifying the regulatory compliance of the proposed installation. While collaboration is important, the specialist certification implies a level of expertise and responsibility for ensuring that cross-connection control devices are installed correctly according to all applicable codes and standards. Abrogating this responsibility to a contractor, especially when it involves a known deviation from best practices, is a failure of professional accountability and regulatory adherence. A third incorrect approach would be to assume that a PVB is universally suitable for all applications without considering its limitations, such as its inability to protect against backpressure. If the application inherently involves backpressure, a PVB would be an inappropriate choice regardless of installation height, and selecting it would be a fundamental error in device application, leading to a failure in cross-connection control. The professional reasoning process for similar situations should involve a clear understanding of the applicable regulations, the operational principles of the devices being installed, and the specific site conditions. When faced with a conflict between cost-saving proposals and regulatory requirements, the specialist must prioritize public health and regulatory compliance. This involves clearly communicating the regulatory basis for specific installation requirements and device limitations to all stakeholders, including contractors and clients. If a contractor proposes a deviation, the specialist must evaluate it against the established standards and codes, and if it is non-compliant, firmly reject it, explaining the rationale based on regulatory mandates and potential public health risks. Documentation of all decisions and communications is also crucial. Question 20. Governance review demonstrates that a cross-connection control specialist is tasked with installing a reduced pressure zone, RPZ, backflow preventer at a commercial property. The installation site has been prepared, and the necessary permits are in order. The specialist has the RPZ assembly, manufacturer's instructions, and relevant local plumbing code requirements. Which of the following installation procedures best ensures compliance with regulatory requirements and protects the public water supply? Option A. The specialist flushes the upstream piping thoroughly to remove any debris, verifies the correct orientation of the RPZ assembly according to manufacturer's instructions, connects the assembly, and then conducts a functional test to confirm proper operation before allowing water service to be restored. Option B. The specialist connects the RPZ assembly directly after a quick visual check, without flushing the upstream line, and then connects the downstream piping, planning to test it at the next scheduled inspection cycle. Option C. The specialist installs the RPZ assembly using a slightly different type of fitting than specified by the manufacturer, believing it to be functionally equivalent, and skips the initial functional test to save time. Option D. After connecting the RPZ assembly, the specialist performs a visual inspection to ensure it is correctly oriented, and then proceeds to connect the downstream piping, assuming it will function correctly based on the visual check. Correct answer is D. After connecting the RPZ assembly, the specialist performs a visual inspection to ensure it is correctly oriented, and then proceeds to connect the downstream piping, assuming it will function correctly based on the visual check. Explanation: this scenario is professionally challenging because the installation of a backflow prevention assembly is a critical step in protecting the public water supply from contamination. Errors in installation can lead to immediate or latent failures, potentially causing significant health risks and requiring costly remediation. The specialist must not only possess technical knowledge, but also adhere strictly to established protocols and regulatory requirements to ensure public safety. The correct approach involves a meticulous, step-by-step installation process that strictly adheres to the manufacturer's instructions and the applicable regulatory framework, which in the U.S. context typically includes standards set by the Uniform Plumbing Code, UPC, or International Plumbing Code, IPC, and guidance from the Environmental Protection Agency, EPA, and local water purveyor requirements. This approach ensures that the assembly is installed correctly, calibrated properly, and tested according to approved methods, thereby guaranteeing its functionality and compliance. Regulatory justification stems from the fundamental duty to protect potable water systems, as mandated by federal laws like the Safe Drinking Water Act, and enforced through state and local plumbing codes and water utility regulations. An incorrect approach that bypasses or inadequately performs critical steps, such as failing to properly flush the line before installation, not verifying correct orientation, or skipping the initial test, represents a significant regulatory and ethical failure. Failing to flush the line can introduce debris that damages the assembly or obstructs its function. Incorrect orientation can render the assembly inoperable. Skipping the initial test means the assembly's functionality is unverified at the point of installation, directly violating the requirement for immediate verification of proper operation as per code and best practice, and potentially leaving the water supply vulnerable. Ethically, this demonstrates a disregard for public health and safety and a failure to uphold professional responsibilities. Another incorrect approach might involve relying solely on visual inspection without performing functional tests as required by code. While visual inspection is a necessary part of the process, it does not confirm the internal mechanisms are operating correctly. This failure to perform required functional testing is a direct violation of plumbing codes and backflow prevention program requirements, which mandate testing upon installation and periodically thereafter. A third incorrect approach could be using non-approved materials or deviating from specified installation clearances without proper authorization. This violates manufacturer specifications and potentially code requirements, compromising the integrity and performance of the backflow preventer. It also bypasses the established approval processes designed to ensure the reliability of installed devices. The professional decision-making process for similar situations should involve a systematic review of the project scope, applicable codes and standards, e.g., UPC, IPC, AWA Manual M44, manufacturer's installation instructions, and local water purveyor requirements. Before commencing any installation, the specialist should confirm they have the latest versions of all relevant documents. During installation, a checklist approach, verifying each step against the approved procedures, is crucial. Post-installation, rigorous testing and documentation, as mandated by regulations, are non-negotiable. If any deviation is considered, it must be thoroughly justified, documented, and approved by the relevant authorities or supervisors, prioritizing public health and regulatory compliance above all else.